Hello.
Hi. Hi, Tariq. Go ahead.
Hi, good. So we are ready to start the session. Okay, it's 10 o'clock here in GMT time. Actually, that confused us because we've got a summer time, which is 1 hour ahead of time. Anyway, so good morning and good evening in Japan. We are ready to start session M3, which is on inspection. There are three papers. The one is about cleaning residual water with a mechanism in sewer pipes before inspection can take place. The other one is about communicating with a mobile robot that is immersed in an oil storage tank, doing inspection of the floor of the tank. And finally, the third paper is about inspecting wind blades with a robot that climbs on the tower to reach the blades. So if we have the first speaker for the first paper, I don't know who that is. Is it Kosuke Uchiyama? Hello?
Sorry, can you hear me?
Yes, we can hear you now.
Oh, thanks for the introduction. Can you see my presentation?
Yes. Are you Kosuke?
Yes, I'm Kosuke Uchiyama.
All right, please introduce yourself and start your presentation.
Thank you. I'll start my presentation. I'll give a presentation titled Residual Water Removal Mechanism for obtaining clear images with sewer pipe inspection robot. This is my presentation agenda. First, I'd like to present the introduction. Storage is an important infrastructure facility in the world. However, the number of aging sewer pipes that have exceeded their useful life of 50 years is increasing. Aging pipes can lead to serious accident as figured 1. So regular inspection of the pipe inside is necessary. Pipe inspection is performed using camera images obtained by special devices. Existing special devices include automated robot like the figure 2 and the push type endoscope like the figure 3. However, considering that sewer pipe are thin, long, and complicated, the devices have problems. Automated robots have difficulty inserting into small diameter pipes and have difficulty passing through bending pipes due to their high rigidity. In addition, as shown in figure 4, the push type endoscope causes friction in the bending pipe, which increases the force required to push in. So it cannot conduct long distance inspection. Therefore, in this study, we established the inspection method for thin, long, and complicated pipes. The sewer pipes that are difficult to inspect with existing devices are the pressure pumping method pipe. Its features are thin, long, and complicated. So especially we focused on the pressure pumping method pipe. In the previous study, earthworm peristaltic movement was focused on. Peristaltic movement is shown in figure 6, and it has 2 advantages. First, it can proceed in a small space because it requires only space for radial expansion and contraction. Second, it can generate high traction force because it has a large contact area with the outer wall. Based on this peristaltic movement, we created pipe inspection robot Pure 5, shown in figure 7. This robot successfully inspected on actual pipes. However, if there is water in pipe, inspection by the camera image is not possible. When the water remains in the pipe, it looks like figure 8. In the residual water, camera images are unclear. So the purpose of this presentation is to develop a mechanism to obtain clear images regardless of residual water. Considering the development of the mechanism, there are two problems. First, the water is clear, the camera images are unclear in the residual water. So it is difficult to clarify the camera image by filtration. And we decided to use a water suction pump to remove residual water from the water intake. Second, if the robot has only one water intake, the water intake will leave the water due to self-rotation as figure 10. For this problem, the water suction intake always need to kept submerged in water. Therefore, the mechanism must solve these problems. Second, I'd like to present the residual water removal mechanism. An overview of the inspection robot mounted with residual water removal mechanism is in shown figure 11. As a residual water removal mechanism consists of a water suction pump and a water suction unit. About this, the water suction pump must be capable of sucking up residual water at the length of 60 meters and a height difference of 4 meters without priming water. And the water suction unit must be capable of sucking water to a level lower than the camera when the head is rotating. So these two topics will be presented. First, let's talk about the water suction pump. From among the many pumps, a vein pump was selected. A vein pump is kind of volumetric pump like figure 12. We chose it because it can suck little water without priming water. The vein pump used in this study is shown in figure 13. This pump is connected to an electric door to drive it. In this slide, I show the pump's basic characteristics. Figure 14 shows the relationship between the rotor speed and flow rate. As rotation speed increases, flow rate also increases. Figure 15 shows the relationship between pump location and flow rate. As distance between pump water intake and the pump increases, the flow rate decreases. So in the experiment, we kept the rotor speed constant and mounted the pump just behind the robot so that the pump and water intakes are close together. Next, let's talk about the water suction unit. The water suction unit must be capable of sucking water until the water surface is reduced to 47 millimeters or less when the robot rotates on the pipe axis. Based on that, water suction unit was developed shown in figure 16. It has two device points. First, two water intakes are provided and their tips are made of silicon tube. From this, if the robot rotates on pipe axis, one water intakes will land on the water. Second, silicon tube and the water suction hose connected through the Y-shaped joint. From this kinking of the suction hoses was prevented from the robot progresses. For more information about where to mount of this unit, as shown in figure 17, we decided to place as a unit between the second and the third unit for the passages of a bending pipe. Third, I'd like to present experiments. We conducted functional verification experiment of the water suction unit. Its purpose is to verify that the water suction unit is capable of handling self-rotation and solid sludge in residual water. The figure 18 shows this experimental environment. We conducted water suction in two conditions. First, it sucked 7-liter tap water. Second, it sucked 7-liter tap water with 2,500 balls, assuming solid sludge. The experiment was conducted by rotating the robot on the pipe axis. In figure 19, we put cloud tape at the head part to experiment with each angle. The table 1 shows the angle of the head part when each color comes to the top. The figure 12 shows the state of the water suction unit at each angle. The water suction experiment is conducted once at each angle. After water suction, we measure the water level in the pipe. The figure 21 shows the water suction of tap water, and the result is shown in figure 22. Water suction time is about 6 minutes, and successfully lower the water level in the pipe to below the target level of 47 millimeter on all 3 times. Therefore, as the target is achieved by sucking water from the water suction unit at an optical optional angle when the robot rotates on the pipe axis. The figure 23 shows the water suction of tap water with air balls, and the result is shown in figure 24. As in the prior experiments, successfully lower the water level in the pipe as shown as figure 24. So therefore, achieve the target in water suction of residual water with solid sludge. Finally, I'd like to present conclusions. As summary, we developed a residual water removal mechanism for pipe inspection robot, and the robot successfully sucked residual water enough for the camera to be exposed from the water. As the future works, the mechanism to remove residual water containing a highly viscous liquid sludge that is difficult to filter with the existing joint attachment will be studied. Thank you for listening.
Thank you very much for an excellent presentation. We now go to a question and answer session. Any questions?
Can I ask a question, Professor?
Yes, please go ahead.
Thank you very much for your presentation. Just want to know what sort of cameras you are using and what's the what sort of defects you are targeting with that.
Oh, sorry. Could you tell me one more time?
Are these special cameras which you're using, and what sort of defects you can detect with those cameras?
You asked me why the camera is in the head part. Is it?
No, the question is what type of camera are you using and what kind of defect are you looking for?
Thank you for asking question. Oh, sorry, I don't, I don't, I don't know about this camera in detail, but this camera is like endoscope camera, but this, but and not, not, so it is different, or different of endoscopes. It can move, use peristaltic movement. Is it okay?
So what kind of defects are you looking for? Are there cracks in the pipeline, or are they caving of the pipe, or is it something else? Maybe clogging the sewer, something getting stuck in there.
We use this camera, and from the we watched camera images, and where is there a break or a crack in the pipe, and we detect from the camera images.
Okay, if you were using ultrasound, it would be advantageous to have water in the pipe, wouldn't it? Because then you would have a couplant to couple your ultrasound to the pipe wall. You could look for cracks that are maybe even hidden.
Yes, we uh, we detect the crack, where is crack, and a break part from this camera, and as future works, we use any other detection methods that is on study.
Okay, thank you for your answers. Our time is up, so we will move to the next paper now. Thank you very much.
Thank you for the listening.
So the next paper will be presented by Richard Anvo. Is he there? Is Richard here?
Yeah. Trying to share now.
All right, whenever
Can you
you're
see
ready.
my screen?
Yes, we can see it.
Yeah, my name is Richard Anvo from London South Bank Innovation Center. I'm going to present today wireless communication with mobile inspection robots operating while submerged inside oil tank storage tank. As state of the art, most of our storage tank today are inspected via data acquisition obtained via umbilical cables. So our work was to look into how we can reduce the size of the cable by using different techniques such as wireless communication. And our work was looking at RF communication investigation. So different frequency study were carried out by looking at different mediums such as crude oil, gasoline, diesel oil, jet fuel, kerosene, and vegetable oil. So was looking also of absorption and dispersion in the medium, and to compare which type of frequency we can use during our investigation. And we come out to use 433 megahertz because was the one which is on the market. But if you use low frequency, you get very good propagation of the wave in the medium, as this table show here. For example, for seawater, the propagation was very bad. The absorption was very higher compared to vegetable oil or crude oil or gasoline or kerosene. Also, the EM propagation path loss was looking between petroleum, medium, and vegetable oil. Here in this work, we use a vegetable oil for health and safety because we cannot have our hands on petroleum medium easily. But looking at this EM wave absorption table, we see that vegetable oil is close to crude oil, gasoline, and kerosene. We use also this software Feko to do simulation to see the attenuation of the wave. So on this side, we got a box which is represents our medium, and the antenna is placed at 3 meters to the medium. So propagating through, we got diesel fuel, jet fuel. So the total gain was showing with this, with this. So what we can say here that the radiation pattern, we got more attenuation in water. So for the jet fuel or diesel or vegetable oil, the wave were penetrating through the medium. Similarly, we was looking at surface current. Again, for 400, for example, 200 megahertz and 300 megahertz, the surface currents was very higher, which means if you use very low frequency for petroleum medium, you can penetrate easily than higher frequency. Again, 433 megahertz was also good as well for the propagation. And the experimental, the lab also was carried out with a vegetable oil. Here we got a receiver, transmitter, and a receiver antenna. So, and the pipe which was filled with vegetable oil. So was transmitting here I don't have a video, but I got the picture which is show, for example, in one hand here, DC motor, and we submerge the transmitter. So was able to turn on the receiver, which is connected to a DC motor successfully. And also was looking at data transmission through vegetable oil. We got 2 antenna transmitter and the receiver connect to laptop. The receiver was submerged to pipe, a small pipe here, which is a steel plate pipe. And the results show that the data transmitter was received without any attenuation in these tables. These are software we developed to check the data transmission to see if we're going to receive any attenuation during the transmission, but we receive all the data transmit through the vegetable oil. Again, we use this system which has been developed in the lab to a real robot environment for localization and navigation. So the localization system represents the antenna, which is 43 megahertz RF, and we use sonar for the navigation, which is mount on the front and the back sonar here for the navigation. And this robot was deployed in oil tank, which is in full image show down here, 4 meter oil tank by the height is 2 meter, full of vegetable oil. Again, it was vegetable oil because of health and safety. So in this one, we got one of antenna was on this robot. So yeah, sorry, yeah. So in this image, the antenna was, the receiver was placed on the top of the tank, free receiver placed on the top of the tank, and we got the one receiver which is connected also to our computer. And then the results for the robot for the localization system show on this display. We see the robot path with the antenna feedback to our receiver is displayed on this image, and the right-hand side image was showing the 360-degree, the back sonar for the navigation, and the front sonar for also for the navigation. So in summary, we have investigated the investigation of radio frequency communication in petroleum and vegetable oil. And the future work is to develop a mini directional antenna, which will be integrated inside the robot for localization and communication. Thank you. Any questions?
Are there any questions? I can ask a question. You have a communication system. So the aim is you've got this, you've got some mobile robot operating inside a storage tank full of oil.
Yeah.
Which is inspection, and you're trying to, one, communicate with it to reduce the umbilical. So you want a wireless communication system. So that's just acquiring data. So you may be acquiring NDT data, but what you're showing here is a localization. Does this mean that you are doing some time of flight measurement with beacons placed outside the tank, receivers placed outside that tank, and the robot transmitting the pulses? How does that work?
Yeah. So we got one antenna which is placed on the robot. It's like a pinger antenna. So it send information for those receiver. So the ping antenna sent each time information for those receiver to capture, to send to the computer software to process, to see the position of the robot each time in the tank.
So how many receivers do you have on the roof of this tank?
I've got three receivers.
And you're doing some kind of trilateration?
Yeah, trilateration.
Okay. And how does that work? How accurate is the measurement?
From now, we process 1,000 of data before we can display on this screen. So from now, the accuracy is not too much, because, for example, we got some data which is outside the tank here. So our aim is to improve the accuracy of this system.
I mean, this is a hugely sort of difficult problem, isn't it? Because you will have multiple paths, multiple reflections within the tank. You have to transmit through the oil medium. Then you have to transmit the wall of the tank, which is a steel tank, I presume. And you're able to receive signals outside in air.
Yeah.
Okay, that would be useful. Any other questions?
Sorry, do you hear me?
Yeah.
Yes, we can hear you.
Thank you thank you, Aman, thank you, Richard, for your presentation. And I have one question. It's about transmitter and receiver. If I understand, your robot receive radio frequency signal under gasoline, yes, and under oil.
Yeah.
And it's maybe not for theme question, but can I use this system for submarine, for underwater robot, for control?
Yeah. If you see here, we did a study a bit on, for example, seawater. So the attenuation, I think, is very high. You have a very high attenuation using water, because we did all those things. It depends. For example, you can do homemade RF, but it will be very hard to, because we know water is more attenuative for the RF. It depends how deep you want to do your inspection also.
Thank you. If I understand, it's more easy than oil, yes, under oil.
Yeah, yeah.
Thank you for asking.
What is the operating word? Is it the dielectric of the medium that determines your transmission or attenuation?
Yeah, the dielectric, I mean, yeah, it's the one who determine the high transmission or low transmission. When, for example, water is conductive, so you get more attenuation. So a dielectric system just is like a less RF pass through without any much attenuation, not a zero, but not too much attenuation.
So sonar would be better in water, wouldn't it?
Yeah, sonar, yeah. Sonar is, yeah.
Okay, thank you. Any other questions? So we let the time run down to 50. Okay, thank you. So we'll move on to the next.
What can I?